Hello, I'm Kotschevar-Smead. This is my Fundamentals of Cybersecurity, Computer Science 327 final project, and it is called C Vulnerabilities. I'll kind of get into what that is later, but first, let's start with some background issue about C to kind of identify what issue I'm trying to solve here. So, we just kind of pull up a Chrome tab. We kind of see some of the things built in C. So databases, compilers, operating systems, GUI, game engines, embedded systems, browsers. Those are just the things off the top of my head and from this website. So the point I'm trying to make here is a lot of things are built in C directly, but a lot of the tools that application software is used that might be made in other languages use a C runtime or are built on top of C. So C is everywhere. And to further illustrate this point, I kind of have a Linux Wikipedia pulled up. You kind of see here that Linux is leading operating system on servers, where 97% of servers worldwide use Linux. That's a lot of servers running on essentially C code, because Linux is made in C. Also, extra, if you happen to have an Android, those phones are also made with Linux and therefore C. So, what is the problem here? So C, if we look at this article here that talks about memory safe programming languages, C is not considered a memory safe programming language. And so essentially what my repository or my project is doing is it's identifying some basic C vulnerabilities, just a couple, not a whole lot. It's identifying some basic C vulnerabilities and it's recommending mitigations. And I also have a section where I demonstrate the C vulnerabilities on an actual Linux server that I SSH into. And I show stuff like getting a shell on the system and escalation of privileges. Just some stuff, some offensive hacking. But the purpose of my repo is to stand as a guideline for people to follow for safe coding practices. So actually, the White House, I have another Chrome tab here. With this, I have a bug, a famous bug, 2014, the Heartbleed bug. It arised from a C buffer overflow vulnerability. But the White House actually urges people to use languages like like Rust, like Go for systems development for now on, because C does propose a security risk. So what are these ads? So I'm closing out this tab. So essentially, if you're a programmer or developer in the future, you should be writing Go or Rust, unless you're me and you have a fantastic repo like mine right here to follow, then you'll be okay. But if you're anyone else, it's probably good to start writing systems level code in a memory safe language like Rust. But like we've identified earlier, that's not always possible. A lot of the legacy code bases, a lot of the legacy tools are made in C, and therefore there's always going to be a need for C developers. So I guess the ultimate goal of this project is for people to look at this fantastic repository that I have here that's, very extensive and covers almost everything that could ever exist about writing memory safe C code. People watch this video 10 times, and maybe the White House will retract its statement saying, hey, C is a good language. You should write, systems level code in C as long as you follow Cayenne's guidelines. So that's the ultimate goal of this project. Maybe that's reaching a little far, but who cares? Let's get into it. So right here, before I show the videos later, further demonstrating the examples, getting deeper into each one of them, I'm just going to go a quick little overview of what each vulnerability I've identified, kind of just talk about it, show some code. So buffer overflow, like I explained earlier. Buffer overflow is a vulnerability where basically you have a buffer and you allocate a space for that buffer or size in that buffer to be allocated on the stack. And basically a buffer overflow is when reading in data or getting in data or filling in that buffer, you have too much data and you don't check the bounds of the buffer. So you end up overflowing the buffer, it's in the name, And that could lead to memory in other locations, such as future addresses, like the memory. It's contiguous memory, anything past that buffer being possibly affected. And this can have some really poor outcomes. So here in this buff unsafe.c, you can kind of, so it's an unsafe C file. It's not really unsafe, but there's potential if, for example, this debug was ever called. I have this input here, and basically I have this function here that doesn't check the size of the input. It's just filling in the buffer. So this buffer is 100 bytes. If I, for example, scan in a 150 character string, that's 150 characters. That'll affect the 50 memory addresses past the 100 in the buffer. So if there's a variable or something important stored after that, that could potentially be bad. Normally programs will throw like seg faults and stuff like that, or the operating system will throw a seg fault, but sometimes these things are uncaught and sometimes they could be manipulated, and it's unfortunate. So buffer overflow, most common. This is kind of a mitigation, a short mitigation you could do to do it, to mitigate it. It's checking the size of the buffer before you input it in. So right here, I'm using a safe function, fgets. It checks the size of the buffer. If it's not the size of 100 bytes in this case, it will just only include the first 100 bytes in that buffer and just get rid of the rest of the data. Same thing here with stir copy. It's using stir and copy, and we're null terminating the string, which is just always a good practice. Now let's go on to concurrency. We'll do a little README. You can kind of see here some vulnerabilities in concurrency have to do with like manipulating data in a way that you don't want it to. So like race conditions, deadlocks. A deadlock is basically when two threads are waiting on each other and they have access to different mutexes. I don't show a mitigation for that, but I kind of discuss some of them down there and a little more in my videos later. Let's start looking at some code. So this is some unsafe concurrent code. I create two threads on this process that each call this function, or they actually call a different function. And they both use this global variable, shared variable. So if you know assembly, you would know that this one line of code and this one line of code are actually like 4 instructions in assembly. So basically, with operating systems, you could have a context switch anytime during those 4 assembly instructions. So it would look like this. It would look like grab from memory shared variable. It'd grab whatever shared variable's address is stored at. It'd load it into register, like W1, I'm on ARM. It'd increment it in the register, and then it'd move it back into memory. But if there's a context switch by the operating system at any point in those assembly instructions, and it uses the other thread next time it runs this process, you could have some potentially bad results with this data. Like it will be inaccurate. So this is really important that concurrent programs actually, return correct results because, it's computer science. Things need to be 100% correct. So safe code here in this case is using a mutex. Right here, we initialize the mutex in the heap. This mutex is basically a lock on the variable. So the variable cannot be incremented or decremented until the lock is released. So if thread 1 holds this lock and it doesn't unlock it, thread 2 will not be able to decrement the variable, blah, blah, blah. So now let's go on to Stack Overflow. And obviously I will talk about these later in my videos when I go into more detail. I'm just trying to get through this right now, just a quick overview. Then we go over Stack Overflow. Stack Overflow is used for kind of like DDoS attacks. It's basically trying to crash a program by just spamming a bunch of memory and creating a bunch of stack frames. We show this in code here. So pretend there's some imaginary user input and it's 100,000 and it calls a recursive function that will create 1,000 bytes on a stack, and it'll keep creating new stack frames with each stack frame having 1,000 bytes allocated on it. That will crash your program because eventually you'll run out of memory in your address space. So that's not a good thing. Obviously, that can lead to some vulnerabilities. So what I do suggest here in mitigations, and I go over other techniques like use heat memory, balance checking, stack canaries. I go over in my safe code, setting a max bound, for example. We set a max depth of 3. So essentially, a user will put 10,000, but it has the and max is greater than 0. Once max reaches 0, which it will after 3 times, so it'll only create 3 stack frames, the frames will start to pop, not allowing for basically infinite stack overflow to be created. So next is use after freeze. If we go over use after freeze, it's basically a program tries to use a pointer after the memory has been freed, and it does some undefined behavior, including like crashes, data corruption, security vulnerabilities. So I'll show it in code because it's kind of hard to understand conceptually. So we have some unsafe program here. We have 2 structs defined, struct A, struct B. Now that I think about it, maybe they should just be of the same side. Maybe I should have made this double, but who cares? So pretend this doesn't exist, pretend this doesn't exist. So we have struct A, struct B, and struct A has a pointer to a safe function that's supposed to be called, and it just prints safe function, and the unsafe function gives a shell on the system, and that's located as a function pointer in struct B. So basically right here in this program, we're allocating space for A, nothing new, but we're freeing A later. But the problem is we're not setting A to null. We're not nulling A. So basically, by not nulling A, pretend this safe function was stored at address 4. We've now freed the memory at address 4. Now, A.safe function still points to address 4, but there's nothing there because we never set it to null. Now, when we create B, let's say this function pointer of an unsafe function is set at address 4 now. Now, as a developer, if I accidentally don't see that A is free later, and I tried to call A of safe function at address 4, and now B's unsafe function was created at address 4, A.safe function will end up calling B.unsafe function because of how memory addresses work and how it was freed. And now B's memory is now there. So this won't crash the program. This will just call whatever memory is at address 4. Now that's really, really bad and can really cause errors that a lot of developers might not be able to see. So the solution to use after freeze is really, really simple, but I recommend some other mitigations here. But the solution is after freeing at A, you set it to null, and then when a developer tries to call the function later of A.safe function, you always check if A is equal to null. So all these null checks are really, really important because they will basically say, all right, if there's nothing there, that means I freed it. So just say it's null. So that is the basis of this repository. I'll go in more in depth in the videos later when I show some of the hacking on with Narnia CTFs. So yeah, that's it.